The evolution of digital world has taken several decades of exponential growth. Today we routinely work with code bases with millions lines of computing logic. The most complex systems have long ago surpassed billion lines of code mark. Moreover, these systems serve as platforms for applications and products developed by millions of their customers. The actual complexity of such digital ecosystems is hard to estimate. One thing we know for sure, it is immense and growing, powered by ubiquitous computing, an Internet of Things which brings to play billions of connected devices capable of processing logic. For decades we have been using the potential of technology in rather crude, mechanistic way. We spent a lot of time and money building systems which offered automation of information processing tasks typical for command and control bureaucracies. These systems resemble a bit the Mechanical Turk. Mechanical Turk is a fake automaton, creating an impression of machine capable of playing chess, at the expense of human player trapped inside its bowels and pulling its levers. But this is changing. The capabilities of digital technologies allow us to build systems which enhance cognitive productivity. They become instrumental for human creativity in science, art, entertainment, or engineering. They enable amazing projects such as Whole Earth Telescope, and bring us closer to mysteries of the universe. And more often, systems we design are capable to learn and adapt to the external environment, customize the way they operate based on external information and context. These smart solutions are clever in the way they achieve goals, and become less dependent on human control, achieving remarkable levels of autonomy in executing tasks. Along with the growing maturity and scale of technologies available for implementing AI, the variety of techniques and tools used for smart solutions is also expanding. I will further refer to this portfolio of methods and tools as smart technologies. So why I believe the wonderful world of smart solutions and smart technologies has an engineering challenge. First, this challenge is not new, or specific for AI. Innovative nature of digital world creates much stronger incentives for experimentation than for optimization of the current practice and technology. What is specific for AI is the unique combination of strong demand, overhyped expectations, and unknowns related to impact smart solutions may have on our safety, job security, privacy, or fair treatment by public and commercial organizations. Also, there is a growing expectation that AI is industrialized, while the current practice related to smart technologies is very much focused on experimentation. Unfortunately, the very discipline of AI is not very well defined. The analysis of research paper references published on AI, made available by Elsevier, shows the complex interdependencies of AI conceptual landscape. Arguably, current research in AI is focused silos of specific techniques and methods, and their applications to various problem domains. Consider examples such as image recognition, speech recognition, machine translation, etc. Not speaking about general AI with its bold promise that once we solve general AI, it will help us solve everything else. We need a more constructive guidance to cope with the demand, expectations and risks. Parts of smart technologies landscape differ considerably. Some of them are well tested and provided as canned goods, available for non-expert designers. Others are still in the early experimentation phase and available only to highly skilled experts with large R&D budgets. A leading example of this category would be AI platforms for general problem solving, such as those developed by DeepMind. Another diversity factor is the diversity of development styles, affecting design approaches. These include scripting, ad hoc analysis, formal systems, service-oriented, event-driven, analytical processing, and genetic algorithms. Researchers focused on evidence-based evaluation of the potential provided by AI, such as Gary Marcus and Ernest Davis, the authors of Rebooting AI, emphasize the necessity of a significant reevaluation of expectations towards AI and the challenges related to its development. Davis and Marcus point out that the world of AI lacks tools that would enable creators of AI-based solutions to apply engineering discipline or at least solid craftsmanship to the product development processes. Drawing from their partially anecdotal insights, some general challenges related to AI-based solutions can be defined. Number 1 is the use case versus AI maturity. Given a specific use case and a set of AI tools and techniques, can we filter out those that provide reasonable, evidence-based confidence that critical requirements for the use case can be addressed? Number 2 is AI-based solution architecture. We need to be able to design solution components, in particular, AI-based components, that are modular, multi-layered, and can be designed and analyzed on different levels of detail against engineering criteria, such as coupling, cohesion, scalability, performance, or reliability. Finally, there is the challenge of AI-based solution maintainability. Solution architecture and applied AI tools need to allow us to monitor and control solution operations and manage solution performance and configuration changes. Also, we need to be able to assess how aspects such as confidence in automated inference or analytical predictions are affected by changes. The necessity to rethink the design of smart solutions is also justified by recognizing the specific risks. The AI solution is typically embedded within a complex system. It may be unclear the exact party responsible for the errors or issues in the model. In most cases, the model developer is only the agent acting on behalf of the principal, the business owner. AI solutions that make autonomous decisions need to resolve ethical and regulatory dilemmas. These lead to moral risks. From the practical perspective, it is hard to evaluate the model accuracy, as the models made decisions based on the estimated probabilities. This can lead to inaccurate or poorly understood decisions. The fact that real-world evolves drives another risks. The model used to drive actions will necessarily deteriorate. The imperative to reflect context changes in analytical model underlying a smart solution adds layer of complexity. Many global organizations recognize the need to manage the AI-based models through respective guidelines. A good example being ethics guidelines for trustworthy artificial intelligence provided by European Commission in 2019. Previous attempts to define the design patterns of smart technologies point to similar principles, such as the need for continuous AI-based model monitoring, the crucial role of human supervision, alignment of the requirements regarding the model to the business case, or compliance with regulatory and ethical rules. As a consequence, apart from methodological developments of the top-rated tools in the area of machine learning and advanced statistics, there is also a significant practical need for governance and standards related to practices of development for AI. The next generation of smart solutions will offer higher cognitive functions than those observed today. To implement them robustly, we need practical standards for design and implementation. Moreover, when discussing the impacts of AI on human work, economics, and social processes, there is a need for another perspective than the one related to AI as a scientific research field. To understand the impacts of AI, one needs to focus on users and beneficiaries and a value delivered by smart solutions. This is the key imperative driving the work on CAST framework, undertaken by our team, combining researchers, practitioners, and technology policymakers. CAST stands for Constructive Approach to Smart Technologies. Our aim is to provide AI community, solution proponents, decision makers, and solution designers a common landscape and language for discussing how various AI techniques and methods can be combined to effectively deliver business value. Our approach is inspired by the concept of pattern language, introduced into the world of technology due to the intellectual cooperation of the object-oriented programming community and Christopher Alexander in mid-90s. Our work takes advantage of AI use case database managed by Global Partnership on Artificial Intelligence. CAST design pattern taxonomy has been successfully tested and applied by GPI as a use case classification tool. CAST is essentially a canvas laid out in two dimensions. The first dimension, modus operandi, shows what emergent behavior is expected from smart solutions. There are two extremes for this dimension. First is autonomy. A smart solution is expected to act as an autonomous agent, driven by a defined plan. Already existing examples include transport of goods or people, manufacturing, providing specific services, such as parking assistance without the need for the human operator as the supervisor. The second extreme is insight. Here a smart solution is expected to provide non-trivial, highly processed, actionable information, effectively supporting the agenda of an autonomous agent. The supported agent may be a human, resulting in a human enhancement solution, or a machine, serving as a part of the digital ecosystem. The second dimension, motive, designates the immediate beneficiary/user of the smart solution value proposition. It can be argued that the ultimate beneficiary of any technical solution can always be traced to a human actor. Nevertheless, we already see conglomerates of connected, collaborating digital cloud services, mobile terminals, sensors, or actuators. Examples include smart cities, smart factories, intelligent utility grids, etc. There is a quickly growing space for smart solutions for which the immediate beneficiaries are machines or other systems in such ecosystems. Again, we see two extremes for this dimension. First, enhanced human solutions deliver personalized services or products to a human actor, enhancing essential human capabilities. We call the second extreme smart digital ecosystems. complex, interrelated, highly automated set of cyber-physical processes. Software engineering has well-established architectural patterns for solution categories such as business intelligence, service-oriented architecture, or web portals. The design factors are well understood, and building a successful solution based on those patterns is a matter of adhering to these good practices. The starting point for cast canvas is a simple combination of the dimensions into a classic quadrant. Such canvas provides first approximation of the smart solution patterns taxonomy, crude smart solution categories. By combining autonomy with focus on humans, we arrive at the area of servant proxies. These are the solutions that replace cognitive and physical work of humans in service relationships with other humans, machines, or infrastructure. Examples are smart home hubs, autonomous vehicles, digital assistants in the areas of sales and customer service, care robots, concierge robots. If we replace autonomy with insights, we arrive at digital coworkers quadrant. These solutions expand or support human cognitive work by providing knowledge and information, supporting decision-making, solving non-trivial problems. These are the superpowers for humans. Autonomous operations platforms is a quadrant where autonomous solutions are built to serve as components for complex cyber-physical systems. These platforms provide various technological and business services. For instance, automated factories and warehouses, or autonomous transport systems for material handling. The need to provide external insight to machine actors leads us to virtualization and management of assets and processes quadrant. Here be solutions that enable the creation of digital simulations of various assets. Such asset simulations are what we often call digital twins. The simulated assets are often tangible, including buildings, machines, or the components of urban architecture. They can also be intangible, such as processes, systems, capital markets. Digital twins enable multiple types of operations on them: event prediction, configuration optimization, operations optimization, and many others. Naturally, this canvas is far too simple to provide a meaningful, constructive support for smart solution designers. It serves just as a foundation. So let me give an overview of the CAST framework structure and some examples of its current content. First, we will see how the dimensions are fine-tuned to provide structure for smart solution subcategories. Our aim has been to define various capability levels for each of the vectors: autonomy, insight, human enhancement, and digital ecosystem support. Next, we define examples of smart solutions for each of the subcategories. Many of them are real-life examples, while some are speculative. Finally, we attempt to provide design factors and design heuristics which should be considered by solution architects and designers. So, let us start with the fine-tuning of autonomy-oriented solutions. In this category, the machine actor executes some end-to-end activity based on the intent or goal provided by the action recipient, who may be human or machine actor. The receiving actor can be seen as a corrective and monitoring agent, rather than as a task executor. We can define the following levels of autonomy that require different design approach and provide different value. First, limited/local autonomy related to the local, immediate context. A mobile robot may autonomously avoid obstacles in response to activities of other mobile agents in the near surrounding, while executing a mission assigned by some higher-level actor. The autonomy of a machine agent can be extended, so that no guidance by the action recipient is required. Recipient just needs to specify explicit goals and intents. The solution can perform long processes selecting near-optimal scenarios and achieving the goals autonomously as long as the context is within tolerance parameters. Otherwise, corrective action needs to be applied based on human intervention. For example, a material handling robot can be asked to unload a truck at the dock and handle the incoming cargo according to their manifests. CAST calls this capability level execution autonomy. The last level of autonomy is called proactive autonomy. A proactively autonomous system can accurately infer action goal and intent from the context, such as when a medical care robot can aid patients, based on their behavior and health sensor data. For insight-oriented solutions, capability levels can also be defined in a similar way. In this category, the machine actor delivers advanced insights, supporting the activities of human or machine recipient. The insights can be provided on demand by the recipient, or in some routine process which is either event or time-based. CAST proposes the three capability levels for insight. Factual insight: the solution can collect and recognize relevant facts, performs orientation out of data, gathers observation, through advanced analytical processing based on defined analytical models or heuristics. Next goes the predictive/adaptive insight. Such solution can apply heuristics and non-trivial extrapolations to infer actionable predictions. Moreover, the solution can assess the adequacy of models and heuristics, and propose, and/or automatically implement changes that increase model quality. The last capability level is the creative insight. A creative insight solution can generate new information or knowledge based on models and constraints. A set of candidate workspace designs based on data such as spatial constraints, user preferences, or expectations related to its purpose. This level is different from the previous one as the smart solution may extrapolate beyond the data points seen in the training set. The capability levels for human enhancement are based on typical approaches to personalization. In commodity approach, personalization, if any, has to be explicitly demanded by recipient. Context-aware solutions deliver personalization based on solution usage characteristics. For example, a smart home can take advantage of different interaction channels, such as mobile speech assistant, mobile alerts, smart home audio, depending on the urgency of message and recipient presence attributes. Finally, a deep personalization can collect data to build deep profiles of recipients to optimize the goals served by smart solutions. For instance, deep profiles and models can be used to provide recipient with optimized physical fitness improvement plans involving activity or dietary recommendations. Smart solutions for digital ecosystems range from edge intelligence, through orchestrators, up to enabling platforms. Edge intelligence provides specialized, non-trivial services for the ecosystem. An example may be a smart traffic camera, capable of identifying objects, or recognize plate numbers. Orchestrators coordinate collaboration of digital ecosystem components, supporting end-to-end processes as well as casual interactions. Enabling platforms are fundamental constructs for digital ecosystems, providing an operating environment for components, uniform governance, access, security, scalability, resource management, or interoperability of services. Fine-tuning of the dimensions spans much richer canvas for each of the smart solution categories. The resulting map allows the smart solution proponents and architect to plan a specific way of delivering value using smart technologies. Its aim is to offer an intuitive way of representing alternative options and evaluate proposed solutions. Let us consider a service such as Google Duplex, a digital agent capable of making a restaurant reservation or hairdresser appointment. It has the capability of casual, friendly conversation, understanding many of the idiomatic phrases used by humans in informal, everyday communication. Maybe extra value could be offered by increasing its autonomy based on a personal calendar, so that all the planned lunch and hairdresser appointments are automatically set up, behind the scenes. Perhaps there is a way to expand the scope of personalization for this service, so that each personal travel will have a proposed itinerary for dining, meeting persons of interest, or visiting places of interest. This line of development follows the path of friction economics, which provides value by eliminating friction created by unwanted, time-consuming tasks, necessary to achieve personal objectives. Or perhaps we are building a smart solution supporting urban mobility management. For this we might build a multi-agent simulator of urban traffic, based on statistics of traffic flows and connection topology. Feeding the simulator with actual traffic data can help us achieve better insights into traffic patterns, and better understanding of how the patterns evolve over time, leading to optimization capabilities. The next step would be to model the needs and preferences of commuters, as well as the constraints related to various urban transport systems. This creates an opportunity to use generative design techniques, and generate realistic, commuter-oriented ideas for urban transportation solutions. As you can see, the map provides opportunity for ideation and evaluation for every category of smart solutions. Also for the more abstract categories related to cyber-physical systems. Moreover, bigger systems can be architected by combining components from different subcategories. Consider a complex smart solution such as autonomous systems supporting internal logistics in factories or warehouses. Such systems often employ autonomous robots as smart, digital workers. Their work is orchestrated by fleet management component, which is responsible for optimization of the transport process. Optimization goals might be diverse, such as energy efficiency, cycle time for order queues, or fleet utilization. Such component may take advantage of insights created by analyzing real-time data from supply chain, or manufacturing execution. Autonomous transport systems change the way material is handled in warehouses and factories. The design of such systems can be supported by simulation tools, which test the performance of different scenarios, and may even suggest optimum configuration for a set of business optimization objectives. The final component may be a platform that integrates all previous components and turns the entire system into just another element fitting the entire smart factory concept. The most important aspect of CAST is the identification of design patterns and heuristics, which should be considered when creating the smart solution architecture. The mission of CAST is not to provide its users a more efficient way to organize a rule set or neural network for a given problem-solving or image recognition challenge. This is what data scientists and AI experts excel at. Our ambition is to help shape smart solutions and apply smart technologies in a responsible way, and we believe that engineering discipline is a foundation on which any kind of responsible approach has to rest. The smartness is inherently an emergent feature, and emergence implies complexity. Establishing some form of pattern language is a widely accepted approach for structuring complex systems. We believe it will become a useful tool to enable responsible design of smart solutions. The pattern language should start with some form of adaptive loop, which underlies the adaptive capabilities, learning, autocorrection, time-based competitive performance, and communication. Out of many constructs that can be found in literature and engineering practice, CAST adopts the OTA loop, envisioned by John Boyd. The OTA adaptive loop involves observation of the environment, interpretation of data, decisions, and actions. OTA assumes that the adaptive system can monitor and improve the models used for orientation and decisions, so that a learning feedback is also part of the construct. Due to its abstract nature, OTA is used only as a point of reference for design patterns specific to smart solution categories. But we believe it provides the entire pattern language of CAST framework fundamental consistency. To large extent, smartness of the solution can be traced to efficiency and coordination of its underlying OTA loops. Let us illustrate the pattern language of CAST framework with example, consisting of conceptual architecture, key design patterns and heuristics. The conceptual architecture faux servant proxies is based on real-time synchronization of two loops that form the framework for its design. First is the cognitive loop of a human actor. The human actor initiates a collaboration with a machine actor by providing, explicitly or implicitly, action goal and intent, and then to be able to assess how the outcomes delivered by machine actor are matching the expected results. Human actor expectations are based on their perception of value proposition, their conceptual models, or the metaphors used in solution design. Second is the execution loop. Machine actor interprets the intents and goals, plans its activities, and executes them through a specific process, following an adaptive loop pattern. Autonomous machine actors and related adaptive loops are usually implemented in the form of components following event-driven service patterns, such as event response model, or time-driven loop service patterns. What makes a machine actor smart is high cognitive performance in a dynamic and changing environment. This means primarily the capability of turning available data into a correct representation of factors influencing actions, such as mission goals, progress, environment, status, and so on. The more independent, efficient, and accurate is this process, and the less human attention and oversight it requires, the smarter it is. What sets smart machine actors apart is the ability to adapt, change the way actions are inferred from the available data. In OTA terms, this means that smartness is driven by cognitive performance in orient and decide areas of the cycle. CAST postulates important heuristics for designing servant proxy solutions. Models used for orientation and decision-making should have an explicit representation in solution architecture, modules, scripts, or configuration data. Model, such as layered and componentized neural network with specific feedback architecture, or a rule ontology with parameters, should be separated from its application, such as neural network trained on a specific datasets, specific rule sets and complex event processing logic. Also, models should be designed for flexibility, by employing parametrization, metamodeling, multi-layered architectures, and modularization, so they can be more easily evaluated, evolved, and improved. Finally, the solution architecture should allow for tracking model performance. This needs to be possible for basic cognitive process performance, such as the accuracy of object recognition and classification by a smart vision system, as well as for holistic system performance, showing how effectively and efficiently the system performs its actions from the perspective of mission goals. This can be achieved either as a part of machine actor logic, or in a separate environment, some form of data lab, where models are evaluated and optimized based on data collected from machine actor operations or simulations. CAST framework in its current version offers similar guidance for all four smart solution categories. A digital coworker is conceptualized similarly to the servant proxy, as an interplay between human and machine actors. In this case, however, the interplay focuses on improving the performance of an information process executed by a human actor, enhancing human actor cognitive productivity. This enhancement is achieved by eliminating activities representing waste and overheads, and providing the human actor with insights or assets that are difficult or impossible for a human to create in a comparable time frame, quantity, or quality. In the case of the digital coworker category, ODA can be also used as a design heuristic. In this case, however, it should be used holistically to design systems involving both human and machine actors' activities. The machine actor would serve as an observation and orientation tool, while the human actor is responsible for decisions and actions, as well as for fine-tuning or otherwise improving the model used by machine actor for delivering insights. This provides reorientation and learning capabilities to the entire human-machine ecosystem. The primary design heuristics for this category is that of knowledge productivity, increase cognitive output, eliminate waste, automate necessary housekeeping activities. The focus on human enhancement is important to avoid traps, where advanced systems are used to control humans and reduce them to providers of low-level skills, for example, executing picking instructions in fulfillment process. Such systems do not constitute valid digital coworkers in CAST taxonomy. CAST is a work in progress. We have tested the framework on a number of real-world use cases provided by Team Experience and platform created by the Global Partnership on AI, specifically the use case repository built by the Future of Work Working Group. Also, CAST takes advantage of existing design practices. There is no need to reinvent wheel. It is much better to start with connecting the dots, and then adding some new ones, where they are needed. This is what makes us believe that CAST may become a useful design tool for all those who want to create value with smart technologies. Our primary goal is to transfer the ownership of the framework to the open community of AI practitioners so that CAST can evolve along with growing experiences and new ideas. We need to solve many acute problems of our civilization. We need to keep on innovating. We can do all this by converting the exponential growth of ubiquitous computing into exponential growth of ubiquitous intelligence. We will be building many new smart solutions. To be successful, we need to build them responsibly. Let us do it together. Do not hesitate to get in touch with the CAST team. We are looking for constructive comments, case study submissions, and we will be happy to help you adopt the framework in your endeavors.